Hi everyone, welcome back. In this video I'm going to show you how to solve a quantum mechanics question specifically on the half-harmonic oscillator. This is a variant of the simple harmonic oscillator. I'm going to be using a method that you may or may not have heard before called the method of reflection. So with that said, let's jump right into it. Particle of mass m has a potential given by Vx. Find the energy of the ground state. Now, normally, the simple harmonic oscillator is just Vx equals 1/2 m omega squared x squared for all of x. But here, it's only that way for x greater than 0. And so you may think, how do we even go about solving this then? You have to remember that all of the information about a quantum system is contained within the wave function psi xt, and the governing equation that we have to solve for that is a Schrodinger equation. IH bar, first derivative of psi with respect to t equals minus h bar squared over 2m. Second derivative of psi with respect to x plus vx psi xt. Now psi is in terms of two variables here, x and t. From the given function of Vx, we see that x takes on values greater than 0 and less than 0. So x is between minus infinity to positive infinity. And it's customary to solve for a wave function at a future time, at times greater than 0. So for the solution to this equation to be physically realistic, we have to impose boundary conditions and an initial condition. What that means is we have to know how psi behaves as x goes to infinity and minus infinity. It's customary to assume that psi becomes 0 as x becomes large in magnitude. So psi at infinity at t equals 0, and psi at negative infinity at any time equals 0. Now this is because the magnitude of psi squared represents the probability density of the particle's position, and the area under that curve has to be 1. So, for the area to be for the area under the curve to be finite, the function has to go to 0 as x becomes large. So these are the boundary conditions for which the solution to this equation, the Schrodinger equation, will be physically realistic. And now we have to know what the function is at t equals 0. So that's called the initial condition. I'm just going to say that psi at t equals 0 is some function called psi 0x. It's not necessary to know how, what this function is. It's just fine. It's good enough to just call it psi 0x. So now that I've set up my problem, I'm going to solve the Schrodinger equation on the intervals for which the potential energy function is defined. So I'm going to start with x less than 0. So the Schrodinger equation for x less than 0. Second derivative of psi with respect to x, and now I'm going to plug in infinity for Vx. Now, the only way this equation can be satisfied with an infinity on the right side is if psi xt equals 0. And not only satisfy this equation, but also the boundary condition as x approaches negative infinity has to be 0. So the solution to this partial differential equation is 0 for all x and t less than 0, for all x less than 0. Now, what that means is, so I'm going to draw the graph of this potential energy function to illustrate what this means physically. So if I draw the graph on positive x, the shape is parabolic. And for x less than 0, it's it's like an infinitely high cliff. So because the magnitude squared of psi represents the probability density, this means that the particle is never to the left of the vertical axis. The particle is constrained to move only along the positive x-axis. So that's what setting the potential energy function to infinity does. It prevents the particle from moving anywhere in the, on the negative x-axis. All right, so now I'm going to solve the Schrodinger equation on for x greater than 0. So IH bar equals second derivative, and now plus 1/2 m omega squared x squared, and this is and also psi xt, and this is for x greater than 0. And because it's x greater than 0, we have to know what psi is at 0. That's we need to know the boundary condition at the smallest value of x. So we get that from this solution here. By requiring that the wave function is a continuous function, the wave function is going to be 0 all along the negative x-axis, and it has to be continuous. So at x equals 0, the wave function has to be 0 as well. So by continuity, this boundary condition is 0 at x equals 0. Now, you might think that the way to solve this partial differential equation is with the method of separation of variables, but that would lead to a problem that we haven't solved before. If in textbooks of quantum mechanics, it's always the solution to the harmonic oscillator is done over the whole line, so from x between minus infinity to positive infinity, and we can make use of those results by using what's called the method of reflection. That's a method that we use to solve partial differential equations on the half line when we know what the solution is on the whole line. So how do we apply that? What we do is we consider the same equation using a different function. I'm going to call it psi bar. It satisfies the same equation. Over the whole line. So we replace this this condition at x equals 0 with one at x equals negative infinity, and we know how psi behaves at negative infinity. It goes to 0. So we can replace this boundary value problem with this one. However, we need to satisfy this what's called a Dirichlet boundary condition. It's the function itself is known at a particular value of x to be 0. And the way we satisfy it is by using the odd extension of this initial condition for psi bar at t equals 0. So at t equals 0, psi bar is going to be the odd extension of the initial condition for psi. So it's going to be, as usual, psi 0x when x is positive. And for x less than 0, it's going to be negative psi 0, negative x. This will make it so that psi is always 0 because psi bar is going to be an odd function. So the solution to this problem has already been solved for in textbooks. Psi bar is a linear combination of the in textbooks it's we use the method of separation of variables here to solve this partial differential equation by using a product solution, a function of x times a function of t. And in solving that with the method of operator factorization, where they introduce the raising and lowering operators, you can derive the eigenfunctions for the harmonic oscillator. They are psi 0, psi 1, x, psi 2, x, and so on. And n goes from 0 to all the way up. So the general solution for psi bar xt is going to be n from 0 to infinity of some constant bn, or a Fourier coefficient, it's called, times psi n x times e to the minus I e n t over h bar. This the wiggle factor is the solution to the ordinary differential equation in t, and psi n is the solution to the time-independent Schrodinger equation that you get when you separate variables. So these solutions are assumed to be known for this problem here. So now I'm going to use the initial condition here to determine Bn, the Fourier coefficients. So I'm going to set t equals 0. So if I do that, I get psi bar x0 equals sum Bn psi n x, and this is equal to the psi bar x0. I'll just call it that. So in order to solve for Bn, I'm going to multiply both sides by psi m x, where this is another eigenstate of the harmonic oscillator. And then I'm going to integrate both sides from minus infinity to positive infinity with respect to x. Oh. So I'm going to bring the constants in front. So this is going to be sum n equals 0 to infinity, Bn, and then integral of psi nx psi m x dx. And the reason I'm doing this is because the eigenstates of the harmonic oscillator are orthonormal. So this integral is going to be 0 as long as n equals 0 for n not equal to m. So every single term in this infinite series is 0 except for 1, the one in which n is equal to m. So it's equal to 0 for n not equal to m, and it's equal to 1 for n equals m. So on the right side we have just Bn, and on the left side we have integral of psi bar x0 times psi nx dx. Oh, I forgot the dx here. So now I'm going to plug in the so because psi bar is an odd function and the integral is taken over a symmetric interval, the integral is going to be 0 whenever psi n is an even function, because the product of an odd function and an even function is odd. So if n is 0, if n is odd, If n odd, then Bn equals 0. Now, if psi n is an odd function, then no, I'm sorry, it's the other way around. So if n is even, then psi n is even, and the product of an even function and an odd function, psi bar x0, is going to be an odd function, and then Bn is equal to 0. If n is odd, then psi n is odd, and the product of an odd function with an odd function is even, and we can write we can write this as double the integral from 0 to infinity of psi bar x0 times psi n x dx. And for x greater than 0, psi bar is going to be psi 0x. So I'm just going to replace this with, I'm going to write it in terms of the initial, of the original initial condition. So this is psi 0x psi n x dx. So n is even, then Bn is 0. So our general solution for psi bar, if we write it over the even and odd numbers separately, so if we take the sum from j equals 0 to infinity b2j psi 2j x e to the minus I2j t over h bar and plus I'm going to start, or start it from 1. And b2j minus 1 psi 2j minus 1 x times e to the minus I e2j minus 1 t over h bar. So for n even, Bn is 0. So this here is going to be equal to 0. So this entire term here is 0. So what this means is that psi bar xt is just the, on the right here, e2j minus 1 psi 2j minus 1 x e to the minus I e2j minus 1 t over h bar. And to get, so we solve for psi bar. Now that we have psi bar, we can solve our original partial differential equation on the positive x-axis by taking the restriction of this to positive x. So psi xt is going to be the same thing. But for positive x. So I know what, for x less than 0, psi xt is 0. And for positive x, psi xt is this formula here. So if I put it all together, psi is 0 if x less than 0, and it's all of this. For x greater than 0. And I can use I can write this compactly by using what's called the Heaviside function theta x. And as you can see, the the energy here of this involved in the wave function is e2j minus 1. This is the energy of the nth eigenstate is n plus a half. So I'm going to plug in 2j minus 1 plus a half times h bar omega. And if I simplify this, this is 2j minus a half times h bar omega, where j goes from 1, 2, and so on. The ground state is the smallest value of the energy, so it's going to be j equals 1 if I plug it in here. So the ground state is E1. It's going to be 2 minus a half, that's 3 halves, times h bar omega. That is the ground state for a particle of mass m with in the half harmonic potential. Thanks for watching.